Hello, greetings to all. My name is Anderson Beber. I'm an applications manager and responsible for industrial water treatment processes, products, systems in Latin America. And today I'm here to share with you some interesting case histories on both automatic knowledge-based control for internal chemical treatment on high pressure boilers, specific for recovery boilers in pulp mills, and also a very new technology to leak detection in those high pressure boilers, specifically for the recovery boilers, but also may be applied to the power boilers as well. As you all know, recovery boilers may be susceptible to small leaks, and those leaks can lead to very undesired accidents, and this is the reason why one must pay very close attention on preventing those leaks, or at least trying to make some track on how those leaks can occur in a given high pressure boiler. So first of all, before we go directly to the controller itself and its features, just a very quick remind on the most common internal chemical treatment in a boiler, which is based on phosphate. Usually it's congruent phosphate, but some changes can be made as well. And the reason for us to utilize phosphate is that you're gonna add some buffering in the internal water to minimize corrosion. This process can occur in an optimized way controlled by an automatic controller. So even if you have very little or even large feed water contaminations, so variability in the quality of the feed water or any other scenario which is harmful for a boiler, the controller will adjust automatically very shortly. So you will not face long-term damages or even short-term damages in the system. Of course, regarding that, you have to treat the contamination itself. So some of the challenges for a internal phosphate corrosion program for the internal boiler water is that you need to keep a minimum buffering environment in the boiler to avoid upsets, chemical upsets in the system. And the most common products that are utilized are usually two forms of phosphate. Usually most plants apply disodium phosphate and trisodium phosphate, but there are some cases that you can use monosodium phosphate as well, or even a blend, a ready pre-blend product, but it's not so good as if you have two products, as we're going to see in the next few minutes. So this is the typical diagram for congruent phosphate for the internal boiler water control, chemical control. And what we see by this diagram is that we have little boxes, and we must keep our boiler, our internal water in the boiler, between those boxes for a given pressure range. And the concept is that if you are able to provide that, you will minimize many different corrosion processes, phenomena in the boiler. Of course, other variables can change, but this is very important and must be kept between the box. This is why many people say in-box time or controlled time in the box for a given phosphate residue and a pH. So the concept here is that let's say we take a lot of samples from the boiler water and we analyze, and the results, the chemical results that we get are those little red dots, as we can see in this orange box here, which is our control range for our boiler, and this specific pressure range. So all those points inside the box, the control box, they are what we call in control, but in box. But this little green one here just outside the orange area is out of the box, so it's not really in control. And our job, either manually or automatically, is to provide the features to move up this little green dot here inside the control box. So basically, let's say we have a given result, which is down here. The red dot is down here, way out, very, very far from the control box. So our purpose is to get it back in control. The same, let's say if it's on the left side here, also our goal is to put that in control inside that boiler. And for one to do that, there are many different tools to do that. Change concentration cycles, change total phosphate dosage, and mainly change the proportion between, for example, disodium and trisodium phosphate. It's not so easy if you do it manually, although it's possible, but it's not so easy. So ideally, what we can have is what we call a knowledge-based control system, which is summarized in this picture that you see right now on the screen. So a controller, which is basically an advanced fuzzy logic controller, will get main data from the system and important data continuously, like water mass balance, so the flow meters, so the amount of water being sent to the boiler and the amount of water being released from the boiler blowdown, continuous blowdown, and of course chemical data like pH and phosphate residuals. So all this data is then calculated and in special algorithms in this controller, which will give a response to the chemical dosing pumps to adjust automatically what are the necessary dosage rates for either products, even if it's necessary to zero one of the products, but this is done automatically by the controller. And the result is like this case history in South America, where previous to the installation of the control system, the automatic control system, this was the result, and the company, the site, was facing a very poor in-box control with only 24%. And just a few weeks after the installation of the automatic controller, it was changed completely. Not only 100% of the chemical data points were in control, but also, as you can see in the picture, it's very concentrated, so very little fluctuation or deviation from a given set point. Also, with this automatic controller, it is possible for one to have the boiler leak detection system as well, which is a continuous analyzer which can detect if there are some signs, indication of a leak, even if it's a small leak. And it's based on two different features. The first one is based on the water balance, which is quite easy to understand based on the flow measurements. So if we have all the three measurements, and if they're reliable, feed water flow, steam flow, and blowdown flow, ideally, in theory, steam and blowdown combined should be the same number as the feed water. So this is what we call a water balance. So the true flow coming in minus the difference of the expected flow divided by the expected flow, that's what we call a balance. So if there's a large difference between the measurements here, that could indicate a possibility of a leak in the boiler. And the other feature, which is also very interesting, is the chemical balance possibility. So if we are applying phosphate, and this is the reason we talked about the phosphate internal chemical program, once we are applying phosphate It doesn't matter if it's 1, 2, 3 different products based on phosphate, but if we can measure the amount of phosphate being dosed directly to the boiler drum or to the feed water, and if you have a possibility to analyze continuously this amount of residual phosphate in the boiler blow down, we have X grams per hour or pounds per hour of phosphate being dosed, and Y grams per cubic meter or ppm or whatever in the boiler blow down, and we can compare the theoretical amount of phosphate that should be in the system and the actual one. So the difference between the expected phosphate residual and the actual phosphate residual will give you may give you an imbalance, which can indicate also a small leak in the system, a small or even a large leak in the system. So to summarize, if both systems, water balance and chemical balance, do not indicate any leakage, so of course the conclusion is that you don't have losses, don't have leakages in the system. If you have an indication from the water but no indication in the chemical balance, maybe your leakage is in the cycled part of the boiler, and so on. So it also can give you an idea on exactly the point in the system, the area in the system that you can have this leakage if it really exists. And I finalize bringing to you two case histories from a plant in South America, a pulp mill in South America. The first case history, as you can see this graph, we took different curves. The green curve, the green line, is the water mass balance. So expected flow with actual flow of water. As you can see, we do have a large number of this imbalance, but we can also conclude that it's almost stable. The blue line is completely different, and we can see a large spike on this imbalance between expected phosphate and actual phosphate in the system. What this indicated to us is that we were having much less phosphate than the theoretical amount of phosphate being dosed to the system. So some verifications are done. It's an indication, but it's not a certainty of leakage. And actually, once it was inspected, the local team could see that actually the pumps, the chemical pumps, were not calibrated properly. So the reason was that once the mechanic or the technicians provided a calibration to the pumps, the leakage signal or indication stopped. So it's actually very good for you also to check on your systems. The second case history is much more interesting because it actually indicated a leak in the furnace and the furnace tubes of a recovery boiler in a pulp mill. We're talking here about nearly 100 bars pressure recovery boiler, and it's a very large one, about 1,100 metric tons of steam per hour. So it's huge boiler. And as you can see here on the graphs, both lines, the green, which is the chemical, the water mass balance, and the blue one, which is the chemical balance, they both spiked dramatically, almost at the same time. So this is a clear indication that if everything is fine on the dosage, on the measurements, on the flow measurements, there is a leakage in the cycle pipe part of the boiler. Let's say the furnace, the boiler bank, and so on. And actually, after a visual inspection, the customer could see and determine that there was really a very tiny little tube leak in one important wall of the furnace, the lower part of the boiler. So very quickly, the system identified this small leak in the boiler. Thank you very much, and I appreciate the time and effort, and I'm available for answers.
Hi, I'm Otto Greis from Andritz, and I will welcome you to listen our presentation about methanol purification air recovery plus case Mönsterås. I will first present you our Andritz air recovery plus chemical recovery concept. Then let's discuss about global methanol markets, and after that let's go into main topic of today, Södra Mönsterås methanol purification and its profitability. The Andritz Air Recovery Plus chemical recovery concept is a product portfolio of pulp mill side stream processes which aim for cost savings and additional revenues from pulp mill side streams. The final target is to get zero waste and zero emission CO2 neutral pulp mill. Our first available processes or product modules are the lignin recovery, mill-wide non-condensable gas handling systems, sulfuric acid production, and then this methanol purification, which we are talking about today. Global methanol markets. Methanol is very widely used commodity in the world. It has over 90 million tons annual demand, and as you can see from this chart, the methanol production has nearly doubled during the past 20 years. It's very widely used raw material in chemical industry, and it's also used in the energy sector as a clean fuel as such, or as blended with gasoline in automotive engines, in marine vessels, or simply as an energy fuel in boilers. And it's also one raw material in fatty acid methyl ester biodiesel production. But when we talk about biomethanol production, only less than 1% of the methanol is produced from biomass or renewable energy sources. Most of the methanol is still produced from fossil natural gas or coal. And this, together with the current directives and legislations, will create very high demand and market potential for biomethanol, now and also in the future. And one place to produce biomethanol is, of course, pulp mill. Methanol formation in pulp mill varies between 6 and 15 kilos per ADT, depending a little bit on wood species and the pulping process. And it's formed mainly in the cooking plant and in oxygen delignification stage. And the methanol ends up in the black liquor and is recovered from evaporation plant fall condensates into raw methanol. And here you can see the typical raw methanol composition. It's very dirty. It has, first of all, quite a high amount of water, but also big variety of other impurities such as sulfuric compounds, ammonia, and alcohols, and of course turpentine in softwood mills. And as such, you can only use this raw methanol to be incinerated either in recovery boiler or in lime kiln. But if you want to sell this methanol outside pulp mill as a valuable side stream, then you need some kind of methanol purification process. And this is what we at Andritz have been developing, designing, and successfully started up in full scale at Södra Mönsterås, Sweden, pulp mill, Södra Mönsterås pulp mill in Sweden. This is our first reference. It's a full-scale plant with over 5,000 tons per year annual production. The raw material is liquefied raw methanol from pulp mill, and the end product can be used either as a fuel or as a biomethanol to be sold out from pulp mill. In general, the commissioning and startup went really well and fast. One important reason for this was these prefabricated modules. So these distillation columns, pipes, and all the armatures were built up as a one single piece in the workshop and then transported as a one piece into workshop and lifted up to its place, ensuring a really fast erection. Another important factor was very close and good cooperation with our fellow customer Tecnicelpa. Of course, when you build and develop something totally new for a first time, you will always generate some problems and difficulties, and there will be challenges for sure. But I must say that we really well defeated all these challenges together, and finally the target capacity and purity were reached faster than ever expected. Laboratory testing was an important role during the whole lifetime of the project, but also having a very detailed and verified simulation model was essential, so that you can really do the scale up from the laboratory scale to the full scale and in a reliable way make heat and mass balances and equipment sizings. With this kind of plant where you treat a mixture of flammable, explosive and poisonous chemicals, it's very important to think about process safety and have safety first mindset. We have many risky components such as H2S and methanol, and the whole plant is ATEX classified. It's also very important to design safe startup and shutdown procedures, especially for equipment flushing, cleaning and maintenance, so that you can avoid all the unnecessary spills and leakages and odors to atmosphere. Personal operator safety is very important. Everyone at the plant must use all the time the personal gas detectors, and there are many fixed gas analyzers located also at the different locations of the plant. In case something would go wrong, it's of course very rare occasion, but if, for instance, let's say relief valve is opening, you must ensure that you don't release any relief fluids directly to atmosphere. You must be able to handle those in a safe way. But when you take these aspects into account in a design phase, you can design very safe and easy to operate plant. Then let's go to the process description. The plant consists of a light purification module and full purification module. The light module already produces very clean methanol, but if you want to go into this final IMCA quality, you need some additional equipment and this full purification part. In the light module, we first feed raw methanol or alternatively stripper off gas to the process. We treat it with sulfuric acid in acidification in order to get ammonia and nitrogen into ammonium sulfate, which can be separated by distillation. We also remove turpentine by decanting and distillate away easily boiling sulfuric compounds. In the full purification module, we then in addition have our patented solvent extraction technology, and we add a couple of extra distillation columns to remove final moisture and ethanol and acetone from the final product to get this IMCA quality methanol. And the benefit of this system is that you can first, for instance, only build this light module, and you can later upgrade the system with this full module if you want. Here you can see some product purity specs. The raw methanol is very dirty, but already having this light purification removes most of the nitrogen and most of the sulfur. And when we then go to the full purification, the final product is very clean. This process is more or less all about distillation and extraction. There are 6 distillation columns or stripping columns and 1 extraction column. Andritz has already a long history and experience on delivering these distillation equipments for methanol liquefaction systems and full condensate stripping plants. So going into this methanol purification is a natural addition to our product portfolio. But then in this full purification process, we also use this kind of novel liquid-liquid extraction where we use paraffinic oil to extract some difficult impurities away from the methanol. And this paraffinic oil is regenerated so that it can be circulated again and again in the process. Profitability. The methanol purification process is profitable. The global methanol price has been approximately $400 per ton, and obviously the biomethanol price is even higher, and the price depends strongly on the local subsidies on it. Already having this light purification process is very feasible, since you can replace natural gas in lime kiln and make the pulp mill totally fossil free. Having the full process has even 3 times higher operating margin, but of course it has a little bit higher equipment cost and steam consumption, since we have some additional distillation steps and extraction column in the process. The final plant capacity cost depends on scope, capacity, and raw methanol composition, and it's good to remember that we can easily scale up this process to all sizes of pulp mills in the world today. The final payback time depends on biomethanol price and subsidies on it, but we can build this plant with very, very competitive and feasible payback time. So as a summary, methanol is very widely used commodity, and especially this biomethanol has very strong market size. And Andritz has developed a full-scale biomethanol plant and started up that plant successfully in Sweden. And this plant can produce biomethanol from chemical industry. Process can be built either as a light or full purification option, and what is most important, this process is feasible and profitable. Thank you.
Hello, good afternoon to you all, and thank you for attending this presentation on Suez MBR membrane bioreactor technology. My name is Filipa Ferreira. I am sales manager for Suez Water Technologies and Solutions in Portugal for the Engineered Systems branch, and also a lead domain expert for water solutions for the pulp and paper industry at European level. I will share my desk and shut down the camera for the sake of the quality of the image. So the agenda for my presentation is as follows. I hope you all see my screen correctly. I will first mention a few words on Suez activity. Then I'll make an introduction to the MBR, the membrane bioreactor. How does it work? What are its main components and benefits? Suez experience in the pulp and paper industry and the performance that we have achieved, namely with MBR. And finally, I'll conclude on the MBR, which we consider is a key component to enable reuse and to meet the most stringent regulations, namely color removal. So Suez activity, Suez Water Technologies and Solutions is the branch that gathers all the groups or the main technologies of the Suez Group for water treatment. We are around 10,000 employees serving both industrial as well as municipal customers. Suez WTS is part of the wider Suez Group, leading player in environmental services. Within Suez WTS, we have a very wide portfolio with renowned brands like Degremont, like Ozonia, for example, applicable to the bleaching step in the pulp and paper industry, as well as effluent treatment in some situations, the seaweed membranes, among others. The MBR, how does it work? What are its main benefits? First, to tell that the MBR is not a recent technology. It has more than 30 years in the market, and its application has grown exponentially in the last years, both in industry to treat complex effluents as well as in municipal worldwide. How does it work? It's quite simple. It's composed of a biological reactor where we have the suspended solids at a higher concentration compared to conventional activated sludge solutions. We are talking about 8 grams per liter of MLSS. This biological reactor is connected to the UF membranes tanks, where we have the Seaweed 500. This is the specific model we have for wastewater treatment, and the models, the hollow fibers, are structured in the membrane cassettes. We have the pump to suck the permeate. The flow will be outside in, and we also have a pump for the membrane scouring air, a compressor. In the link below, you can later on click and see the functioning of the membranes. The MBR is more efficient than conventional systems, and we can see why. On the top, we have a conventional multi-step tertiary treatment with an inlet screening step, a primary clarifier, optional, it's not always the case, followed by an aeration basin, a secondary clarifier to make the solids liquid separation, and then a sand filtration. With the Seaweed MBR treatment process, we can immediately see that it's much simpler. For a start, the screen, we here have to work with a fine screen between 1 to 2 millimeters, but we do not always have to have a primary clarifier. We have the aeration basin, which can be exactly the existing one, followed by the UF membrane tank. This combination of aeration basin plus UF membrane makes the MBR. And out of the MBR, which is a constant physical barrier, we have a very high effluent quality for discharge or for reuse. So the process flow diagram is much more simple, more compact, and we reach a higher effluent quality. One of the benefits, earlier I said that we can work with a higher concentration of MLSS in the biological reactor. Indeed, we can work with at least 8 grams per liter. This is usually the design criteria. We can work from 8 to 10 to even 12, whereas in conventional activated systems with activated sludge, we are working with 3 to 4. So immediately we can increase the capacity, the treatment capacity, with the same biological reactor volume. This is an example of a conventional plant footprint with the blue outline. and the impact that the MBR is able to reach. So we reduce at least by half the footprint. So the MBR is the best in class really regarding footprint. It allows for the lowest footprint. It's very easy to retrofit. So we can upgrade existing plants either for capacity expansion or to increase the quality of the treated effluent or to implement reuse. So it's a low-cost opportunity to upgrade existing systems. Other features are that the MBR is the core technology that allows for the highest advanced treatment targets, because it is very simple to combine with other technologies. For example, for hard COD removal or color or phosphorus removal, we can add treatments. For example, we're talking about coagulation. We can do the chemical coagulation directly in the biological reactor and then do the separation thanks to the UF membranes. Also the PAC MBR, this is an example of an MBR configuration where we add powder activated carbon to the biological reactor to remove hard COD. This is very common, for example, in the refining industry. It's a very robust technology because we have solids retention all the time. There's no risk of solids escaping like we have in secondary clarifiers. Therefore, it protects any downstream polishing technology and leads to the lowest solids and lowest fouling potential. The experience we have in the pulp and paper industry. So Suez has worked with different streams, either a single stream like the bleaching stream or a combined effluent like the final wastewater. We are aware of the impact of the different pulping processes or bleaching methods. For example, the sulfide process leads to higher loaded effluents than the kraft process. We are also aware, as different studies were undertaken, of the impact of the wood, of the raw material, either it's pine, birch or eucalyptus. And of course, considerations have to be taken into account whether we're working with old or new mills, namely footprint, for example. The hard color, hard COD, or relate mostly to color, to lignin compounds in the pulp effluents, we see that the range that we have to treat can vary quite significantly. We are also familiar with the different removal rates according to the technologies that are applied. In many cases, there are requirements to remove nutrients like nitrogen, phosphorus, or specific compounds. And all this scenario leads to the need for advanced technical solutions. Which solutions are the best for COD removal? So this is really a case-by-case approach. We have studied almost the complete portfolio of options, from coagulation, sorption to electrocoagulation, through ozone or advanced oxidation processes and membrane processes. In each, we have reached different removal rates and had to consider different pros and cons. By far, the membrane solution, the MBR, eventually coupled with RO, is the one that leads to the highest COD removal in many cases, with complex effluents, we're talking about 92, 94%. Achievable results. So this is the case of a kraft mill, where we have very low levels of solids, lower than 3, because sometimes it's the detection limit. The COD also very good, lower than 200. This is really case by case, depending on the process. For example, sulfide processes, we would reach higher values, but then we can combine with a technology that I'll mention later ahead regarding lignin removal. BOD, the BOD removal, just like the solids, is complete, full. The color is also a very interesting impact. We can go lower with an advanced treatment further on. And all the other parameters, as you can see, are very impressive. Less than 2 ppm for nitrogen, 0.5 for phosphorus, and others. This is a case study in the pulp and paper industry where very stringent discharge limits were being applied, as well as limitations on the flow that could be discharged. So the MBR proved to meet all quality targets in a very robust way, even under variable operation conditions. Advanced effluent polishing trials were performed with very good results regarding COD, color, and salinity removal. The MBR is key component to enable wastewater reuse and to meet the most stringent regulations, in particular color removal. As I've mentioned before, the MBR is the ideal technology when we are considering water reuse, because it produces the highest treated effluent quality and allows to feed directly the wastewater to a polishing system. In this example, we have an RO unit with the goal to reduce conductivity, to allow for reuse in cooling towers makeup, in boiler feed, back into the process or the process water treatment plant, or other applications like, for example, irrigation. Another possibility is to further treat organic compounds that are hard to degrade associated to lignin. So most of the hard COD we have seen for pulp effluents that it is related to lignin. I cannot share a lot of information with you on the LRP in this forum, but of course, if you are interested, we can we can disclose more information on direct discussions case by case. So in this slide, we have a simplified diagram of the wastewater treatment plant composed with a lead primary. This is a compact solution and very efficient system for solids removal that could replace a conventional physical chemical primary treatment prior to the MBR. After the MBR, the effluent is fed to the LRP, and the treated water out of the LRP can either be sent to further polishing step to reduce conductivity, like the RO or the EDR, electrodialysis reversal, or sent to discharge safely to the environment. We can achieve very high removal rates for COD. In the LRP process, we're considering more than 80%. This is what we have seen. And globally, so the MBR plus the LRP, we're talking about an almost complete COD removal, up to 98% in total, which is very high. And this is important when we are facing very stringent discharge limits, like, for example, COD under 100 ppm. This treatment leads to a waste stream that is roughly from 1 to 3% of the feed, and can be sent to, for example, the black liquid evaporator on site. In the photo below, I have 3 samples that illustrate the efficiency of the color removal. It is quite striking. So the sample in the middle, number 2, is the effluent out of the MBR, still with some color, roughly 300, 400 ppm units of color. On the left-hand side, we have the water, the effluent out of the LRP, absolutely color-free, fully transparent, and the waste stream, as we can see, highly colored, so with a high COD content. As mentioned before, it can be sent, for example, to the black liquor evaporator. So this is an example of a polishing treatment that is available for you. As a summary, the MBR technology has proven its simplicity. In a few steps, we can reach very high effluent quality in a robust, stable way, and it has performed in various areas of the pulp and paper industry. It leads to the highest effluent quality at the lowest footprint. It is also a way to expand, upgrade, and refurbish existing plants in a cost-effective way. As it produces no solids out of the MBR and ensures the lowest fouling potential, it is the ideal system to use before for combination with an advanced treatment technology. So thank you for your attention, and I'll be very happy to answer to your questions in the Q&A session. Thank you. Bye-bye.
Hello. I don't
Hello,
know
good
if you're
afternoon.
hearing me. Okay, that's good, because before I started the speech of my life, it's good to know that everybody's hearing me, and there was some problems in other sessions, so everybody's is hearing, so we can start with this session. To start off, I would like to thank very much all the speakers to delivering these presentations, very interesting presentations in very crucial areas of our processes, and showing us really mill cases and mill applications of a very interesting process that are changing our process and improving our processes. Also, we have a very good regional presence from Scandinavia to Brazil, and examples from Portugal, which is very good to welcome here in this session. And also, just to give a very fast word for I'm replacing a colleague, James Blades, that unfortunately had to do some surgery. I hope that is recovering well, and all my good good wishes for his fast recovery. I think it's not very complicated, but it was not possible for him to moderate this session. I hope to do it well. Fortunately, we have a lot of questions, so all the presentations were very interesting, and everybody is participating in this Q&A session, and I'll go directly to the session, to this picking up some questions and asking our speakers. Starting with Filipa, because Human Day is every day, so today is still Human Day. I start with Filipa. And we have here one question that's always come up with this membrane technology, and it's related with lifetime, and I would add up with the fouling management, let's say, of these membranes during the operational time. And we start with this question, and then I'll go to the other speakers, and maybe and then come back with the others. Okay, Filipa,
okay,
if you
thank
want.
you. Sure. So the typical membrane lifetime is 10 years. There are maintenance procedures that have to be done. Of course, there is a CIP system working continuously, and there are 2 times a year deeper cleanings of the membranes to ensure lifetime. To give you a typical number, we're talking about roughly 10 years. Although we have many plants, both in municipal as well as in industry, that are still working with the original membranes with more than 20 years. So in terms of the life expectancy, it's quite a long one. Okay, I hope this answers the question.
Yeah, I think so. Going to Otto, thank you for being here. One of the questions, I think it's still answered during your presentation, but maybe you can clarify for the audience. And the question is, what type of solvent is used in the liquid extraction?
Yes, we use high boiling point paraffin coil solvent. So it consists of alkane hydrocarbons.
Okay, the direct question I think you mentioned during your presentation, but still it's good to clarify with your audience. For Anderson, I welcome to this session also. It was our first question is if it's possible to integrate this controller that you clearly explained into the DCS system of the mill, or it's an independent system. We are not hearing Anderson, at least I'm not.
The sound is not okay.
That's right. No, Anderson. We're still not able to hear you. I don't know if it's any of your local definitions or. I ask our technical people to try to solve it. Meanwhile, I just jump a little bit and try to come back for Anderson a couple of minutes from. For Filipa, also one question that is popping up here in this in our Q&A is the what kind of treatment or destination. I think you also mentioned during the presentation you can do to the concentrate part of LRP or reverse osmosis in this process to recover water.
So for the reverse osmosis, we have to check on salinity, if it's viable to discharge together with other effluents, and in some cases to check mostly on phosphate limits. There are ways we can recover it. So there are RO units for concentrate effluents, so you can desalinate the RO reject and create an even more concentrated stream with a smaller flow rate. So for the RO, there is a solution, an additional RO, or look into the possibility to discharge because it's mostly salts.
Okay, yeah.
For the LRP, the destination we suggest is whenever viable, as it is a small amount of the feed, to concentrate it further in the black liquor evaporator.
Okay, thank you. I'll come back now to Anderson. I think the technical problems are solved. Let's hope. And okay, we're reading now, and come back to the first question, that if it's possible to integrate this controller in the DCS system.
Yes, the controller itself is going to be separated to the DCS system. However, it's a common practice for you to have all the data from this specific controller being seen at the DCS as well. It will not control the variables, but you can see the results and the graphs and the alarms.
Okay, so it's integrable, at least for that part.
Yes.
Thank you very much, Anderson. I'll come back for Otto. There's there having a lot of action here in the Q&A, and I'm trying to to address almost all the questions. There's also here a question about for Otto about if it would make sense to scale up an operation of this type from let's say different neighbor mills in the proximity, and to share this type of installations if there was proximity and this opportunity.
Yes, that totally makes sense. You can mix feeds or raw materials from the different mills together and scale up this process. It's very easily to be scaled up. Another option is to have separate light purification modules in different locations and then have a one big full purification part for all these light processes. But yes, it's totally makes sense.
It makes sense. Okay. Coming back to Filipa, there's questions about how it compares the MBR specific flux per area on this application, and is it in this or not a concern of performance?
Hello, Luis. I think I lost you for a while.
Sorry. But the question was around the MBR specific flux area, and if the presence of fibers can bring problems to this type of membranes.
No, so we have to work on the pretreatment. The fine screen at the inlet is very relevant, but this is similar to every industry and to every application. We have to always watch out for the initial fine screen. It should be within 1 to 2 millimeters, and then for the specific flux for the membrane area flux. It's also a design criteria that is, hello?
Yep.
I think you lost me for a while.
No, we're listening.
No? Okay.
Yes.
Okay, so for the design criteria for the flux, it applies equally to all type of effluents. So we have to design the biological reactor in such a way that the BOD is fully removed. And for the hydraulic design, so for the membrane area, we have to look into the flow rates and apply the typical fluxes. Okay, so there is no specific flux to this paper effluent.
Okay. Thank you, Filipa. Coming back to understand this leakage approach that you showed us, it's very interesting. Still, I think it's even in the example you showed, it still have some sensibility to instrumentation and instruments. How can we integrate this in the approach, or to take account with this in this type of approach to try to leakage, saying that we are dependent on flow meters and a lot, at least some instrumentations that we know that have always some errors and problems like that.
Yes, you're correct about that. Since it's a calculator, you calculate based on measurements, either the flow measurements or the phosphate residue in the system. So if the measurements are wrong or they present some errors, the result of that calculation is also going to be wrong. So the key to address that is to maintain a strong policy of calibration and even replacement of sensors and analyzers, and also the controller itself. If it alarms, the number one item in the list to check is if there's some possible measurement errors. So it actually helps you on identifying if you have any problems in your measurement systems.
Yeah, it can help on that detection. So you don't jump immediately to the conclusion that you have a leak.
Exactly.
You should go for the.
We must say that it's not a certainty of leak; it's a possibility of leak.
Okay, yeah, that should be beared in mind. Thank you very much. For Otto, also some interesting questions. In the presentation, you mentioned that it's used I think liquefied raw methanol, or but my question is that what if we don't have any system, what we usually have, it's a stripper of gases that we collect and send to the recovery boiler or lime kiln. Is this system ready to receive these strip offer gases, or you need additional process to do it?
We can also use directly this stripper off gas feed. Then we just need to have an auxiliary condenser which condenses the gases into feed tank. But you don't need to have necessarily methanol liquefaction system before this process.
So the condenser would be enough to get you the raw material for this installation in this process?
Yes.
Okay. Just to keep another question that is being mentioned is ammonium sulfate a byproduct also, or you have to in some way dispose it?
Yes, ammonium sulfate is a byproduct. We feed it directly as a water solution into the effluent plant, and it's actually acting there as a nutrient for the bacteria and microbes.
Okay, you do it in the same plant. In the same plant, you pump it to the wastewater treatment system. I think we have some problems with the connection with Otto, but we also finished our time for questions. Thank you very much. It was a very interesting session. I hope that all our attendants take a good session and profit of all these very good technical presentations that we had. Thank you very much, and hope to see you all soon. Bye.
Thank you very much. Bye.
Adeus.
Wow.
Obrigado.